The first of the special cases of the second order step response for this low-pass filter is the case where the poles are both real and widely separated. So we're examining the case of a very small Q factor here. With this sort of circuit, this is the frequency response we would expect. There's one pole here causing the amplitude response to drop around 20 dBs per decade, and another pole here which increases the gradient to about minus 40 dBs per decade. And for this circuit, with these values, this is the step response that we would get. You may notice that that looks very similar to a first order step response, the type of waveform we see when we're just charging up a capacitor through a resistor and we don't have an inductor in the circuit at all. I'll return to that thought a little later. For now, it's interesting to note what the effect of each of these terms in the step response is. If we take P1 as being the pole with the higher break frequency, then this term here is going to be positive, since both the numerator and the denominator will end up negative, and it will be decaying quite quickly, because P1 has quite a large negative value. So this would be sort of doing this kind of thing as its contribution to the step response. Whereas this term here is negative. P1 is negative, but P0 is much less negative than P1. So the denominator here might be something like minus a kilohertz minus 10 kilohertz. It's going to end up positive. That makes this whole term negative, and it's decaying somewhat more slowly because P0 has a lower break frequency than P1. So it might be doing something like this. And taking a lot longer to do its decay. It also starts off much larger, because the magnitude of this at the beginning is going to be P1 over the difference between the two poles, and P1 has a larger break frequency than this one. This will be a much smaller contribution than this one. If you add all these contributions up, then you end up with the step response, which, as you can see, does look quite like a first order step response, except right at the beginning. You may remember that when we derived the boundary conditions, those simultaneous equations that allowed us to work out the constants in the step response formula, we had to use the fact that the rate of change of the output, dx dt, at x equals 0, at t equals 0, was equal to 0. So the gradient of this resultant here, just after the step arrives, is 0. And that is not the same as a first order step response. But sometimes you have to look very carefully to see that difference. If we look at this circuit in the simulator with some typical values for the components, you'll see that the step response does indeed look very like a first order step response, one of those exponential rises. You have to zoom in quite a long way to see that actually, just after the step arises, the gradient is 0. There's a gradual ramp up into the gradient, and that doesn't happen for a first order response. You can click the memory checkbox there and it will store the current step response and draw it up in a light blue. If I get rid of the inductor now, then I have something that really is a first order response, and it looks almost exactly the same until I zoom up right to the beginning of the step responses and you can see the slight difference. The first order response has a corner, a distinct change in gradient after the step arrives. The second order step response does not. It's a smooth ramp increase. But once it starts moving up, then with these values, you really can't tell the difference at all. And what's happening in these cases of a very low Q factor is that this green contribution here, the contribution of this term, the pole with the higher breakpoint, is so small and so quick that it's over before you can almost notice that it's there. And this leads to something called the dominant pole approximation. We can say that the step response is approximately just a first order step response dominated by the pole with the lower break frequency. In this case, this one here. And further, we could say that since P0 is so small compared to P1, in the case of very low Q factors, where the poles have very different values, we can approximate this as 1 plus P1 over minus P1, and that is approximately 1 minus e to the P0t. And that is a first order step response. We didn't write it quite like that when we were looking at first order systems. We would write it like this, where Tc is the time constant. However, we noted that the time constant was just minus 1 over the pole. So actually, the two expressions are the same. That's the interesting thing about very small Q factors and two distinct real poles. Next time, we'll have a look at the rather more complex case of two complex poles.